Hello and good afternoon friends, welcome to the CEC EduSet live lecture. Dear friends, since the previous year we have been carrying a series on chemical reactivity and mechanism, and I would like to tell you all that we have contributed a lot on this series. We have conducted numerous sessions, numerous lectures under this very series. We try to understand about the various aspects and the perspectives under the series. Dear friends, taking this series forward, today we are going to talk on amines. We would be talking on the structure of amines, the types of amines, and we would be discussing how amines are prepared. So dear friends, I would like to tell you all, we have again with us within our studio right now Dr. Vandana, who is Assistant Professor in Department of Chemistry, the Aryl Singh College, University of Delhi, and as you all know that she has been carrying this series very successfully. The way we used to get the feedback through you, that you are getting immense knowledge through this series. I hope that you would be successfully studying the content which we are providing through this particular series. So without wasting any time, I would like to welcome our guest, Dr. Vandana. Dr. Vandana, welcome once again to the CEC EduSet lectures.
And good evening all of you. Today in the series of chemical reactivity and mechanism, I would like to discuss about the aliphatic amines, their structure, types of amines and their preparations. In this lecture, I have taken some points which are introduction of amines, nomenclature of amines, structure of amines, stereoisomerism of amines, isomers of amines, preparations of amines and physical properties of amines. Amines are organic derivatives of ammonia, we all know it, in which one or more hydrogen atoms have been replaced by hydrocarbon groups which can be alkyl, aryl or cycloalkyl. Primary, secondary and tertiary amines are the three classes of amines that can have 1, 2 or 3 hydrogen groups bonded to the nitrogen atom called amino, imino and tertiary nitrogen atom respectively. These groups may be identical or may be different. These are the different types of amines. You can see the structure of ammonia, in which nitrogen is bonded to 3 hydrogen atom, primary amine in which 1 hydrogen is replaced by R group, secondary amine or we can say 2-degree amine in which 2 hydrogen atom has been replaced by 2 R group, so on, tertiary amine, and in quaternary ammonium salt not only 3 hydrogen atom has been replaced by R group, but 1 additional R is also there, which giving the positive charge to the nitrogen atom. Hence, it is known as salt with X minus. This is quaternary ammonium salt. Quaternary ammonium salts are those ammonium in which positively charged nitrogen atom is bonded to 4 identical or different hydrocarbon groups. For example, CH3 whole 4 N plus Br minus, that is tetramethylammonium bromide. Saturated aliphatic amines are those in which nitrogen atom is bonded to 1 or more alkyl groups. Here are some examples like methylamine, ethylamine, dimethylamine, ethylmethylamine, trimethylamine. Aromatic amines or aryl amines are those in which nitrogen atom is directly bonded to 1 or more aromatic rings. You can see in the structure in aniline, NH2 group is directly bonded to benzene atom, benzene group compound, diphenylamine 2-degree amine, N-methylaniline again 2-degree amine, N dimethylanilene 3-degree amine. Heterocyclic amines are those that contain the nitrogen atom as a part of the ring. So you can see the examples of heterocyclic amines. First is pyrrole, then pyrrolidine, pyridine, piperidine and quinoline. Next point is the nomenclature of amines. 2 types of nomenclatures are there for any kind of compound. First is common name. Common names of amines are obtained by citing the common names of the hydrocarbon groups. For example, alkyl, aryl or cycloalkyl attached to the nitrogen atom in the alphabetically order and then added the suffix amine. The entire name will be one word. If 2 or 3 hydrocarbon or group attached to the nitrogen atom which are identical, then you have to add the prefix di or tri and so on before the name of the group. You can see the first structure here. Isopropyl group is attached to amine, so isopropylamine. When tertiary butyl group is attached to amine and methyl, then its name will be tertiary butyl methylamine. Diethylamine, triphenylamine, and you can see another structure, tertiary butyl ethyl methyl amine, so on, benzyl dimethyl amine and cyclohexyl ethyl amine. So you have to nomenclature according to the longest chain of the amine. Aromatic amines mostly have special common names. Here are some examples: aniline, which can also known as phenylamine, N-methylaniline, methylphenylamine, orthotoluidine, which can also known as orthomethylaniline. As you can see, methyl group is attached to aniline in ortho position, or meta-anicidine or meta-methoxyaniline. According to IUPAC nomenclature, primary amines are named by adding the suffix amine to the name of hydrocarbon attached to the nitrogen, and you have to omit the E from the hydrocarbon's name. For example, alkane means you have to omit the E and alkanamine. Thus, aliphatic amines are named as alkanamine or cycloalkanamines, or aromatic amines are named as arenamines in case of benzene derivatives, benzenamines. However, the name aniline is also accepted as a systematic name for the benzenamine. Here are some examples. You can see CH3NH2, one methyl group is there, methenamine, ethyl group is there, ethenamine, propyl group is there, propane 2-amine, because amino group is this alkyl group is attached at the second position, then butane 2-amine, next 2-methylpropane 1-amine, 2-methylpropane 2-amine, and you can see other examples also. Now the structure of amines. Nitrogen atom in amines is sp3 hybridized. You can see in the structure of ammonia, methylamine and trimethylamine. And you can also see the bond formation between nitrogen hydrogen, between nitrogen and CH3, and between trimethylamine. You can see that nitrogen as well as all three methyl group are sp3 hybridized, and so bond angle will be same. But in case of methylamine, you can see different bond lengths and bond angle also. In ammonia, same bond angle and bond length will be same, as the attached group towards nitrogen are same. So this is the table which compare the bond length and bond angle between ammonia, methylamine and trimethylamine. In 1, 2 and 3 degree alkyl amine, the carbon nitrogen sigma bonds are formed by sp3 orbitals linear overlap. In 1 degree and 2 degree amine, the nitrogen hydrogen bonds are formed by sp3 1s orbital linear overlap. In CH3NH2, the NH bond angle is slightly less than tetrahedral. Why it is so? Due to the stronger repulsion of NC bond pair and lone pair of electrons. Consequently, HNC bond angle in methylamine has greater value than tetrahedral angle. In trimethylamine, however, CNC bond angle has a value 108 degree due to repulsion among three bulky methyl groups. Next heading is the stereoisomerism of amines. Owing to the tetrahedral geometry around nitrogen, an amine with the three different substituent on nitrogen is chiral because of its non-superimposable on its mirror image. The nitrogen atom is the center of chirality, and the lone pair of electrons on nitrogen atom is treated as the different atom or group, or which is known as phantom atom, with the lowest priority according to the Can-in-Gold Prelog nomenclature rule. Thus, ethyl methylamine is chiral and has two enantiomers, both are aptically active. However, most chiral amines including ethyl methylamine exist as non-resolvable, means we cannot resolve the racemic mixture which contains both kind of enantiomers unless there is a chiral carbon in the molecule. The racemic mixture cannot be resolved because two enantiomers rapidly interconvert at ordinary temperature because of pyramidal inversion through a planar transition state. How it is so? You can see the example in the structure. You can see the two enantiomers of ethyl methylamine. First one is S, sinister, tetrahedral configuration and pyramidal shape. So, you can see both the enantiomers interconvert via transition state because it is having the pyramidal structure, or we can say pyramidal inversion. Thus, numbers 1, 2, 3, you can see 1, 2, 3, 4 indicate the priority of the groups according to the CIP sequence rule. On the other hand, if an amine possesses a chiral carbon atom instead of chiral tricoordinated nitrogen atom, the two enantiomers of the compound are stable and do not undergo interconversion. Hence, the racemic mixture of that compound will be resolvable. Such a chiral amine is butane 2 amine, in which carbon number 2 is the chiral center. You can see these are resolvable enantiomers. One is R according to the priority level of the groups attached to the carbon, and one is S. Now, stereoisomerism of quaternary ammonium salts. Nitrogen atom, all we are aware, that is positively charged in quaternary ammonium salts and have 4 different substituents attached to the nitrogen, which is chiral, and it has 2 enantiomers which are not interconvertible to each other. Inversion of configuration is not possible because the nitrogen atom has no lone pair of electrons and cannot adopt a planar transition state. The chiral nitrogen is thus configurationally stable. The racemic mixture of such a salt, for example, you can see the structure benzyl ethyl methyl phenyl ammonium iodide, has been resolved. Now, isomers of alkanamines. Alkanamines are saturated acyclic compounds having general formula CnH2n plus 3n. Alkanamines can have isomers within the same class and cannot have isomers with other classes of the functional group. For examples, they can be only amines, they cannot be isomers with a different functional group. Methenamines, CH3NH2 has no isomer. Ethenamine is isomeric with N-methylmethenamine only. So, there are only 2 isomers with molecular formula C2H7N. Isomers of C3H9N, you can see there are 4 constitutional isomer. Number 1 is propane 1 amine, propane 2 amine, N-methyl ethenamine, and N-dimethyl methenamine. Isomers of amines of the molecular formula C5H11N. You can see the possible stereoisomers, constitutional isomers of the amine. There are 8, 4 primary, 3 secondary and 1 tertiary amine. First one is butane 1 amine 1 degree, butane 2 amine with 2 enantiomers, 2-methylpropane 1 amine 1 degree, 2-methylpropane 2 amine 1 degree, N-methylpropane 1 amine 2 degree, it is non-resolvable. N-methylpropane 2 amine, it is again a 2 degree, 2 enantiomers are possible and non-resolvable. N-ethyl ethenamine 2 degree and N-dimethyl ethenamine 3 degree. Another isomers for C5H11N, there are 8 primary amines possible, 6 secondary amines excluding stereoisomers and 3 tertiary amines are possible for this particular molecular formula. Next is the preparations of amines. First is methods involving N-alkylation of suitable nitrogen compound, which include alkylation of ammonia or amines, ammonolysis of alkyl halides. Primary amines can be obtained by heating primary alkyl halide with excess of concentrated ammonia or alcoholic ammonia at 100 degrees Celsius in a sealed tube. This is the representation of reaction. Alkyl halide when reacts with ammonia, followed by SN2 mechanism, substitution nucleophilic bimolecular. First of all, you will get the addition product. This is alkyl ammonium halide, which on reaction with NaOH will give you primary amine. If ammonia is not used in large excess, you will get a mixture of all 3 kinds of amines and their ammonium salts. The ammonium salts would result because the reaction does not stop after a single alkylation. Such a reaction is not synthetically very useful because sometimes we need only one kind of amine, but here we get the mixture of amines. So, the over alkylation can be minimized by using a large excess of ammonia. This is again the representation of the reaction, and examples are here. Ethyl iodide, when reacts with ammonia, it will give you ethyl ammonium iodide and then ethylamine. Another example is benzyl bromide, which will give you addition product benzyl ammonium bromide, and then it will give you benzyl amine. And this method was developed by Hofmann, is therefore called Hofmann ammonolysis method. Aryl halides are usually unreactive. However, aniline is prepared industrially by the reaction of chlorobenzene with ammonia under 65 atmospheric pressure at 200 degrees Celsius in presence of cuprous oxide. Secondary amines may be prepared by the reaction of excess of primary amines with primary alkyl halide. Here is the reaction. First of all, you get the ethyl methyl ammonium iodide and then you will get the ethyl methyl amine. Tertiary amines may be prepared by the reaction of excess of secondary amines with primary alkyl halide. Here is the example. Diethyl amine, when reacts with methyl iodide, it will give you diethyl methyl ammonium iodide, and further reaction with NaOH, it will give you a diethyl methyl amine. Next preparation is the Gabriel synthesis of primary amines, very important reaction. In this method, phthalimide is converted by means of ethanolic potassium hydroxide into its salt, which on heating with alkyl halide gives N-alkyl phthalimide. This is then hydrolyzed to phthalic acid and primary amine by heating with 20% hydrochloric acid under pressure or by refluxing with potassium hydroxide solution. When hydrolysis is difficult, the alkyl phthalimide can be treated with hydrazine to give the amine. It is very useful method since it gives a pure primary amine and improved by using the dimethylformamide as a solvent. Here is the representation. You can see the phthalimide first of all reacts with potassium hydroxide. It will abstract the proton and you will get the potassium phthalimide. Then it reacts with ethyl iodide with SN2 mechanism and it will give you N-ethyl phthalimide, that is potassium is replaced by the ethyl group, and then two kinds of reaction can be possible. With KOH it will give you potassium phthalate with ethylamine. If hydrazine is react, then hydrazinolysis will take place and you will get the ethylamine along with phthalal hydrazide. These are the another examples of Gabriel phthalimide synthesis in which you can synthesize benzylamine, glycine. Next is the alkylation of ammonia with primary alcohols, that is ammonolysis of alcohols. Simple primary alcohols of low molecular mass react with ammonia in gaseous phase under pressure at 350 to 450 degrees Celsius in the presence of alumina or thoria as a catalyst to give a mixture of amines 1 degree, 2 degree and 3 degree. The primary amines may be made to predominate by using a large excess of ammonia, then further alkylation is done. Methylamine and ethylamine may be prepared industrially by this method. Phenol reacts with ammonia at 3 degrees Celsius in the presence of anhydrous zinc chloride to give the aniline. Next is the indirect alkylation of primary amines via sulfonamides. So, first of all we have to produce the sulfonamide addition product and then after hydrolysis it will give you the desired product. You can see first of all ethylamine, it is react with para-toluene sulfonyl chloride in presence of NaOH. You will get the addition product N-ethyl para-toluene sulfonamide, which will give you the salt, and then further by SN2 mechanism with SCH3I or methyl iodide, you will get the N-ethyl N-methyl para-toluene sulfonamide, which on hydrolysis will give you ethyl methyl amine along with sodium para-toluene sulfonate. Alkylation of sodium cyanamide and subsequent hydrolysis. Sodium cyanamide is alkylated with primary alkyl halide to give the dialkyl cyannamides. The subsequent hydrolysis by aqueous acid or alkali yields secondary amines. Here is the structure you can see. Sodium cyanamide first of all reacts with ethyl iodide by SN2 mechanism. So, you will get the diethyl cyanamide, which on hydrolysis will give you diethyl amine. Next is the alkylation of aniline and subsequent nitrosation and hydrolysis. Aniline is alkylated with primary alkyl halide. Here we have taken the methyl iodide to yield NN dialkyl aniline, and the subsequent treatment with nitrous acid yields para-nitroso NN dialkyl aniline, which is then boiled with aqueous sodium hydroxide to give a secondary amine. You will get here dimethyl amine. Next reaction is the Ritter reaction. It is an important method for preparing primary amines with tertiary alkyl group. This reaction is mainly depends on the formation of intermediate carbonium ions. The alkyl cyanide is treated with tertiary alcohol, or we can also take the alkene that can produce carbonium ion in the presence of concentrated sulfuric acid to yield N tertiary, here tertiary alkyl acid amide. The subsequent hydrolysis gives a tertiary alkyl amine. You can see first of all methyl cyanide first of all react with tertiary butyl alcohol in presence of H2SO4 will give you N tertiary butyl acetamide, and then it will give you sodium acetate along with tertiary butyl amine. In place of alkyl cyanide, RCN, HCN can be used. You can see this is another reaction which shows the mechanism how first of all carbonium ion is formed, and then there is a formation of product after hydrolysis. Methods involving reduction of suitable nitrogen compound. First of all, reduction of nitro compounds. Both aliphatic and aromatic primary amines can be prepared conveniently by reduction of corresponding nitrogen compound. The reduction may be accomplished with either hydrogen in presence of nickel, palladium or platinum, tin and HCl, SN2 and HCl, zinc and HCl or Fe and HCl. Lithium aluminum hydride is the most effective reagent for the reduction of nitroalkanes. Aromatic nitro compounds on reduction with LiAlH4 gives azobenzenes but not the amines. Nitroalkanes can be obtained from alkyl halides by reaction with silver nitrite. Aromatic nitro compounds are more readily obtained by the nitration of aromatic ring with concentrated HNO3 in presence of concentrated H2SO4. These are the examples. You can see ethyl iodide first of all react with silver nitrous acid to give the nitroethane, which will further reduction by lithium aluminum hydride to give the ethylamine. Next is the N-propyl iodide, which will give you first of all 1-nitropropane, and which on reduction with hydrogen and nickel will give you N-propyl amine. Another example is benzene, first of all nitrated by HNO3 along with H2SO4 at 60 degrees Celsius will give you nitrobenzene, and with reduction palladium and charcoal it will give you aniline. Next example is the benzaldehyde, which is nitrated by nitrating mixture. Here you will get the metranitrobenzaldehyde, which is reduced by tin chloride and HCl, and further by NaOH reaction it will give you the meta-aminobenzaldehyde. Another example is there, first of all reduction is done nitrobenzene, and then with reaction with NH it will give you aniline. Nitrobenzene on reduction with lithium aluminum hydride will give you trans-azobenzene. Reduction of nitriles. Primary amines can be prepared in good yield by the reduction of nitriles either with H2S gas in presence of ranitol, lithium aluminum hydride in dry ether or sodium and ethanol. Reduction of nitriles with sodium and ethanol is called Mendius reaction. Alkane nitriles are obtained from primary and unbranched secondary alkyl halide by reaction with sodium cyanide. Aryl amines cannot be prepared by this method, but benzylamine can be prepared by the reduction of benzonitriles. These are the reactions. First of all, aniline gives you N dimethyl aniline when react with methyl iodide, and then it will give you para-nitroso N dimethyl aniline along with when react with sodium nitrite, and then with NaOH along with the heat it will give you para-nitrosophenol and dimethylamine. Next example is benzyl chloride will give you beta phenyl ethylamine when react with sodium cyanide it will give you benzyl cyanide, then on reduction it will give you amine. Next is the reduction of azides. Primary amines are also obtained by the reduction of alkyl azide with lithium aluminium hydride or hydrogen in presence of nickel or palladium. Alkyl azides can be prepared from alkyl halides or tosylate by reaction with sodium azide. Here is the representation of the reaction. First of all, aniline will give you N dimethyl aniline, which we have already discussed in the last slide. Next is the reduction of oximes. Reduction of oximes of aldehydes and ketone with either lithium aluminium hydride or hydrogen in presence of nickel catalyst or sodium and ethanol gives primary amines. Aldoxime and ketoxime are obtained in good yield by the reaction of aldehydes and ketones with hydroxylamine. You can see in the reaction acetaldehyde first of all will give you acetaldoxime when reacts with hydroxylamine, and subsequent reduction will give you the particular amine. Next reaction is the butane 2-on, first of all will give you the oxime, and then after reduction it will give you the amine, that is butane 2-amine. Another example is cyclohexanone, first of all will give you cyclohexanone oxime with hydroxylamine, and then with reduction with sodium and ethanol it will give you cyclohexanamine. Next reduction is the reduction of amides. Primary, secondary and tertiary amines can be prepared by the reduction of primary, secondary and tertiary amides respectively with lithium aluminium hydride in hot ether or hydrogen in presence of Rann-nickel as a catalyst. Lactams are reduced to cyclic amines. What are lactams? Lactams are cyclic amides. You can see the examples. First of all, methyl chloride, benzyl chloride will give you ethylamine and benzylamine. Following reactions are. Another examples, benzyl chloride first of all will give you N dimethyl benzenamide, and then it will give you benzyl dimethylamine on reduction. Another example is also here. Next reduction is isonitrile, reduction of isonitrile. Secondary amines with N-methyl group can be prepared by the reduction of alkyl or aryl isocyanides. The reduction is carried out either with lithium aluminium hydride or hydrogen in presence of nickel, sodium and ethanol. Alkyl isocyanides are obtained from alkyl halides by reaction with silver cyanide. Both alkyl and aryl isocyanides can be obtained from corresponding primary amines by reaction with chloroform and ethanolic KOH. A primary amine can be eventually converted to secondary amine with N-methyl group. You can see these are the reactions. Ethyl iodide first of all will give you ethyl isocyanide when reacts with silver cyanide, and which on subsequent reduction will give you ethyl methylamine. Benzylamine will give you benzyl methylamine, and aniline will give you N-methyl aniline. Hydrolysis of isocyanides with aqueous yield primary amines. Reduction of alkyl isocyanates, secondary amines of type can be obtained by the reduction of alkyl or aryl isocyanates with lithium aluminium hydride in dry ether. Alkyl isocyanates are prepared by the reaction of alkyl halides with sodium or silver isocyanate. So, these are the presentation of reaction. Ethyl iodide first of all will give you isocyanate, then further reduction will give you ethyl methylamine. Another example is also here. Example of phenyl isocyanide first of all will give you isocyanate with mercuric oxide, and then on reduction we will give you N-methyl aniline. Another examples are here. Example of ethyl iodide, first of all will give you isocyanate, then it will give you ethylamine, and another example is there with benzyl isocyanate will give you benzylamine, that is aniline. Reduction amination of aldehydes and ketones. Primary, secondary and tertiary amines can be prepared from aldehyde and ketones by their reaction with ammonia, primary amines and secondary amines respectively, in the presence of reducing agent such as hydrogen in presence of ranuncular sodium cyanoborohydride. The process is called reductive amination because amination is done over here as well as reduction is also done over here. That is why it is called reductive amination. The intermediates formed in the reactions are imines and substituted imines and iminium ions respectively. These are readily reduced to 1 degree, 2 degree and 3 degree amines respectively by the reducing agent. Sodium cyanoborohydride is used as the reducing agent and reduction is known as Bock reduction. This is the example with acetaldehyde, it will give you ethylamine. First of all will give you acetaldeimine and benzaldehyde will give you benzaldimine and which will on reduction will give you benzylamine. Acetophenone will give you alpha phenylethylamine, cyclohexanone will give you cyclohexylamine. Synthesis of secondary amines, you can see benzaldehyde when reacts with aniline, it will give you benzyl aniline. Acetone when reacts with ethylamine, it will first of all will give you N-ethyl acetoamine and then on reduction it will give you ethyl isopropylamine. Next example is the phenyl acetaldehyde. When reacts with primary amine, that is methylamine, it will gives you N-methyl phenyl acetaldehyde and then on reduction with sodium borocyanide, it will give you N-methyl beta phenylethylamine. Another example is also here with cyclohexanone along with ethylamine, it will give you cyclohexyl ethylamine. Examples of synthesis of tertiary amines. Acetaldehyde when reacts with secondary amine, that is dimethylamine, first of all will give you the iminium hydroxide ion and then it will give you N-dimethyl ethanamine. Cyclohexanone will give you N-dimethyl cyclohexanamine. Tertiary butyl amine when reacts with formaldehyde and formic acid at 100 degrees Celsius, it will give you tertiary amine. The two other variations of reductive amination are, first is Eschweiler Clarke methylation reaction. N-methylation of primary amine or secondary amine to a tertiary amine or R NCH respectively by reaction with a mixture of formaldehyde and formic acid is called Eschweiler Clarke reaction. This is a reductive amination procedure using formaldehyde as the carbonyl group and formic acid as the reducing agent instead of nickel and hydrogen. Formic acid is oxidized to carbon dioxide. And you can see pyrrolidine will give you the N-methyl pyrrolidine. Next reductive amination is a Leuchart reaction. When aldehydes or ketones are heated with ammonium formate or formamide at 180 to 200 degrees Celsius, primary amines are formed. Secondary amines can be obtained using N-alkyl ammonium formate or N-alkyl formamide. Similarly, tertiary amines can be obtained using either N-dialkyl for ammonium formate or N-dialkyl formamide. Ammonium formate serves to supply some ammonia, a aminating agent, and formic acid as reducing agent. You can see the examples. Acetophenone when reacts with ammonium formic acid, it will give you alpha phenylethylamine, and cyclooctanone when reacts with N-dimethyl formamide, it will give you cyclooctyl dimethylamine. Methods involving rearrangement of acyl group. Primary amines can be prepared by the following three types of reaction, which are very famous reaction: Hofmann, Schmidt and Curtius reaction. All these three reactions involve the formation of acyl nitrene intermediate which undergoes rearrangement to alkyl isocyanate. This will be your another intermediate, and the subsequent hydration yield unstable N-alkyl carbamic acid, which decomposes to a primary amine and carbon dioxide. First, I will discuss about the Hofmann bromamide reaction. It is a very good method for the synthesis of amines. Primary amides when heated with bromine and alkali. For example, we are taking here potassium hydroxide yield primary amine containing one carbon atom less than that present in the starting amide. So, this is the beauty of the reaction. For this reason, the reaction is also called Hofmann degradation, because you will get the product one carbon less. And here are the examples. With propionamide, when reacts with bromine and potassium hydroxide, it will give you ethylamine, and with benzamide it will give you aniline. This is the mechanism of the reaction. First of all, the proton is abstract by the base. You will get the nitrine intermediates, and after removal of bromide ion, you will get the acyl nitrine, in which there is a rearrangement of the group. A chiral R group migrates with retention of its configuration. That is, if a starting product is R, the intermediate will be the R. It will gives you alkyl isocyanate, which on hydrolysis will give you carbamic acid. I have already told you it is your unstable product, which will give you primary amine. Next reaction is the Schmidt reaction. It is not a good option because of its fatalness. Carboxylic acid reacts with hydrazoic acid in presence of concentrated sulfuric acid to give primary amines having one carbon atom less than the starting carboxylic acid. Hydrozoic acid is generated in situ because of its instability by the reaction of sodium azide with sulfuric acid. These are the examples. Hexanoic acid will give you pentane 1 amine and benzoic acid will give you aniline. This is the mechanism. First of all, acid is acidified the proton. You will get the protonated acid. It is attacked by the hydrozoic acid and it will give the nitrine, which on removal of water molecule will give you the acid azide, in which there is a rearrangement of migration of the group, that is R group, to the electron deficient nitrine, and then you will get the isocyanate, which is protonated, and which on hydrolysis first of all will give you carbamic acid and then primary amines. Next reaction is the Curtius reaction. Acyl azides on heating in benzene or chloroform yields alkyl isocyanates, which on treatment with water give primary amines containing one carbon atom less than the present in acyl azides. So, among all the reaction you can see the product will produce with less number of carbon atom. Acyl azides are obtained by reaction of acid chlorides with sodium. So, these are the examples. You can see acid chloride first of all will give you acid azide, then isocyanate will form, which on hydrolysis will give you primary amine. You can see how acyl azide can be prepared. Ester first of all reacts with hydrazine, will give you acid hydrazide, which on reaction with nitrous acid will give you acyl azide. Another example is butanoyl chloride, when reacts with sodium azide and chloroform, it will give you propane 1 amine. This is the mechanism of Curtius reaction. First of all, you can see there is a formation of acyl azide with sodium azide. You can see how the addition product is formed, and then there is a migration of R group. So, you can notice among all these three reactions that there is a migration of all R group towards the electron deficient nitrogen atom with the retention of the configuration. This point must be noted, and then you will get the alkyl isocyanate, which on hydrolysis will give you amines through carbamic acid. Next is the physical properties of amines. About physical properties: methyl amines, ethyl amines, dimethylamine. and trimethylamine are all gases at room temperature. Higher amines are colorless liquid. Amines with relatively high molecular mass are solids. Volatile amines usually have unpleasant odors. Boiling point, amines are polar compounds. You know why these are polar? Because of the nitrogen-hydrogen bond. Primary and secondary amines can act both as hydrogen bond donors and hydrogen bond acceptors because they possess nitrogen and hydrogen bond. Nitrogen being electronegative atom, it can accept the hydrogen. So they form intermolecular hydrogen bond. Tertiary amines can act only as hydrogen bond acceptors but not as hydrogen bond donors because they do not possess nitrogen-hydrogen bond. So they cannot form intermolecular hydrogen bond. For this reason, primary and secondary amines have higher boiling points than isomeric tertiary amines. Amines have higher boiling points than alkanes of similar molecular mass. You can see the comparison of boiling points. For N-butylamine, its mass is 73 and boiling point is 77.8. Diethylamine, same molecular mass but its boiling point is 56.3. Ethyl dimethylamine, molecular mass 73 but its boiling point is 37.5 degree. And N-pentane have boiling point 36 degree with molecular mass 72. Isopentane have molecular mass 72 with boiling point 27.8. So primary and secondary amines have higher boiling points than ethers of comparable molecular mass. This is because 1 degree and 2 degree amines form intermolecular hydrogen bond but ethers do not. Amines have lower boiling points than alcohols and carboxylic acid of comparable molecular masses because nitrogen-hydrogen covalent bond and hydrogen-nitrogen-hydrogen bond is weaker than OHO hydrogen bond. The plain line represents the covalent bond, it must be noted, while the dotted line represents the hydrogen bond. The nitrogen-hydrogen bond is less polar than oxygen-hydrogen bond because nitrogen is less electronegative than oxygen. You can see how the intermolecular hydrogen bonding possible in amines. In diethyl ether, molecular mass 74 and boiling point is 34.5 degree. In diethylamine with molecular mass 73, boiling point 56.3. For N-butylamine, mass is 73 while the boiling point is 77.8. For normal butyl alcohol, mass is 74 while boiling point is 117.3. And for propionic acid, mass is 74 and boiling point is 141 degrees Celsius. So you can see the intermolecular hydrogen bonding how affect the boiling point of the compound, and you can see the intermolecular hydrogen bonding in carboxylic acid, in alcohol and amine. Now solubility. All the amines, whether it is primary, secondary or tertiary, form hydrogen bond with water. For this reason, amine containing up to 5 carbon atoms are highly soluble in water. The solubility decreases with increase in the size of the alkyl group, and higher amines become almost insoluble in water. Lower amines are also soluble in alcohol and ether. Aromatic amines are almost insoluble in water but are soluble in organic solvents such as ether, benzene and chloroform. And you can see the structure hydrogen bonding between primary amine and water, between secondary amine and water, tertiary amine and water. Now the basicity of amines. Amines can act both as Bronsted and Lewis bases because they possess an unshared pair of electrons on nitrogen atom. So they are weak bases but are strongest bases of all neutral molecules, for example water, alcohol, ether and amides. In aqueous solution, they pick up a proton from water to a small extent, producing alkyl ammonium ion and hydroxide ion. Thus, the aqueous solution becomes slightly alkaline due to presence of hydroxide ion and turns the red litmus paper blue. This is also used in the laboratory lab for this kind of exercise used in the lab for the treatment of or identification of amines in a particular mixture or compound. So, here you can see the equilibrium exists in aqueous solution and K will be equals to R-NH3 product of R-NH3 plus and hydroxide ion divided by product of R-NH2 primary amine and water molecule. The strength of base called basicity and expressed in terms of constant, basicity constant, which is given by the expression K is the equilibrium constant and water is the molar concentration of H2O within big bracket is the concentration of molar concentration of water, which is considered to be a constant quantity. The greater the value of Kb, stronger is the base to which it refers. For convenience, Kb is usually expressed in terms of pKb. pKb is the minus log 10 Kb. Smaller the value of pKb, stronger will be the base. The major factor that determines the strength of a base is the stabilization of the conjugate acid. So, we must understand how can we define that a particular basicity of a compound in the form of stabilization of the conjugate acid. Greater the stability of conjugate acid of a related base to the free base, greater is the strength of the base. This relative stabilization in turn depends on the structure of the base and the nature of the solvent which is used. These aspects are considered and discussed here. First is the effect of structure and solvent on the basicity. First effect is the inductive effect and the basicity of aliphatic amines. Aliphatic amines are stronger bases than ammonia. Why it is so? Because the electron releasing plus I effect or due to inductive effect of alkyl group in primary amine increases the electron density at the nitrogen atom and makes it more effective in capturing a proton. Moreover, the plus I effect of the alkyl group stabilizes the conjugate acid, that is R-NH3 plus or alkyl ammonium ion. While the conjugate acid ammonium derived from ammonia has no such stabilization because there is no R group, no alkyl group, no plus I effect is there. So, no stabilization is there. Hence, primary amine is more basic than ammonia due to presence of R group, due to presence of plus I effect, due to presence of stabilization of conjugate acid. You can see the presentation of the effects. Primary amine will give you, when reacts with proton, will give you alkyl ammonium ion. We can say it is a conjugate acid of that particular base, free base. Obviously, the increasing number of alkyl group on the nitrogen atom will increase the strength of base progressively. In other words, we can say, and we should expect the basicity should be in the order, that is 3 degree amine must be more basic than 2 degree and 2 degree amine or secondary amine must be more basic than primary amine because of the greater number of alkyl group attached to the nitrogen atom. So, due to increase in the number of alkyl group, plus I effect will be increasing, but since the order of stability of corresponding conjugate acid is 1 degree amine will give you alkyl ammonium ion and then this will give you ammonium ion. Indeed, this has been found to be so far for the methylamine in the gas phase. In the gas phase, the basicity will follow this order. Ammonia will be the least basic and then primary amine, secondary and then tertiary. However, what is observed in the solvent aqueous solution case, the order of basicity in aqueous solution is found to be as follows. Basicity of amines in aqueous solution for ammonia and for when the R group is methyl group, you can see the order. Ammonia will be the least basic, then tertiary amine, then primary amine, then secondary amine. And when we are taking the another group, that is ethylamine, the order of basicity for amines will also different. Why it is so? I will explain you. The basicity of amines in aqueous solution does not solely depend on the inductive effect, that is the number of R group. It is also depend upon the solvent effect and steric effect. Meanwhile, it may be pointed out that the presence of a group that shows minus effect decrease the basicity of amines. For example, CF3 का whole thrice N is less basic than CH3 का whole thrice N. The powerful minus I effect of CF3, that is due to fluoride ion in this compound, makes it virtually non-basic. Why it is so? Because it does not form salts even with the strong acid because of its stronger electronegativity effect. You can see in CF3 and CH3 when attached to nitrogen atom, it is the weaker base. When hydrogen replaced by fluorine, basicity decreases due to the minus I effect, while basicity increases due to the plus I effect. Next effect is the solvation effect, which influence the order of basicity of amines when in aqueous solution. The basicity of an amine depends on the net stabilization of conjugate acid. The conjugate acid is stabilized by plus I effect of the alkyl group and also by the solvation with water through hydrogen bonding. As the number of alkyl group increases on nitrogen atom, the stabilization of conjugate acid will increase due to plus I effect, hence basicity should be increased. On the other hand, as the number of alkyl group increases, the number of hydrogen, you must note at this point, the number of hydrogen atom on nitrogen decreases, consequently the stabilization by solvation decreases. Moreover, solvation becomes more difficult due to the increasing steric hindrance by the increase in the number of alkyl group. Hence, the basicity tends to decrease. So, you can see sometimes it decreases the basicity due to solvation effect. Thus, as we go along the series NH3, then primary, then secondary and then tertiary, the net effect of introducing successive alkyl group is the increase in the basicity, but the increment becomes smaller and smaller until a changeover takes place on going from secondary to tertiary, where the basicity shows a decrease instead of an increase. You can see the overall effect of stabilization for a conjugate acid. In first compound, you can see when nitrogen is surrounded by 4 nitrogen atom, or we can say ammonium ion, there is no plus I effect as there is no R group and 4 hydrogen bonding is possible. When 1 hydrogen is replaced by ethyl group, so we can say plus 1 plus I effect, inductive effect, and 3 hydrogen bonding is there. When 2 hydrogen atom are replaced by ethyl group, then 2 plus I effect and 2 hydrogen bonding effect is there. And when 3 hydrogen atom has been replaced by ethyl group, you can see there are 3 plus I effect and 1 hydrogen bonding. So, overall stabilization of conjugate acid will decide the basicity of that particular amine. That is why this is the order of basicity in aqueous solution. The order of basicity in methylamine is somewhat different due to the smaller value of plus I effect of methyl group, and in a solvent in which hydrogen bonding cannot take place, such as benzene or chlorobenzene. One would again expect the basicity to increase in this order. Due to increase in this, it has been indeed found that chlorobenzene, the order of basicity of N-butylamines is like this. So, we can say the basicity of amines can be decided by the net stabilization of conjugate acid, that is decided by the inductive effect, the solvation effect and hydrogen bonding. In the next lecture, probably I will discuss about the rest of the physical properties of amines and the reactions of amines. Thank you.
With this note, thank you ma'am. Thank you so very much for giving us a productive session. And dear friends, if you want to give your feedback regarding this particular lecture, or if you have any queries, then you can mail us at info.cc@nic.in. Very soon we are going to upload this lecture on YouTube for your access. We would be meeting again. Till then, take care. Goodbye. Thank you ma'am. Thank you so very much.